the enumerator variant, and they're all equivalent. We've shown that with these three corollaries, right? The if and only if, they go both ways. They're all equivalent. They have the same power. They all three of these variants can what's the word? They all describe, recognize, whatever, the same class set of languages. Okay, so you don't have one that's more powerful than the other, and yeah, that's the sort of been saying here. Now, these variants we've had, they're models, if you like, paper, pattern pencil, paper type models of computers that perform general computation, programmable general purpose computers. Okay? And so we've given several variants, variations of the Turing machine model, and we've shown them all to be equivalent in power. Equivalent means well, they do the same job. If one machine, one variant recognizes a certain language, well, the other variant will also, and vice versa. Okay. Now, there are other models of general purpose computation. Some of them are similar to Turing machine. Let me give you a little bit of history. There was an American, I guess you'd call him a mathematical logician, fascinated by Hilbert's challenge. I've mentioned this a bit before. Fascinated by Hilbert's challenge to the so-called, well, Hilbert was German, so Entscheidungsproblem, which is German for decision problem, and that is, how could you define a procedure, a way, a method, an approach to decide? That's what Entscheidung means in German, decision, decide. Entscheiden in German means to decide. How could you create a way that would allow you to decide whether a particular mathematical statement, call it a theorem, if you like, could be logically deduced from a set of axioms, mathematical type axioms, and together with rules of logic, rules of inference, for example, like modus ponens and modus tollens. In other words, if you're given if A then B and you're given A, well, therefore you can deduce, using this rule of inference, logic, deduction, you can deduce B. And modus tollens is if you're given if A then B and you're given not B, well, then you can deduce not A. Okay, so modus tollens. So given a set of axioms and these kinds of rules of inference, for example, modus ponens and modus tollens and others. For example, not P is the same as P. So rules of inference. So how could you go about given some statement? How could you prove from the axioms and the rules of inference? And these axioms are about mathematics or arithmetic. That's more powerful than just simple addition, because you can, well, what I'm about to say can be done for addition, but it cannot be done, thanks to Gödel, cannot be done for arithmetic powerful enough to do addition and multiplication. So there seems to be some thresholds between an arithmetic complicated, powerful enough to do addition, and another set of axioms more powerful that allow you to do arithmetic with addition and multiplication. Anyway, what Hilbert was asking, find some method that would allow you to prove in other words, decide whether a statement, some mathematical statement, can be deduced from the axioms and the laws of inference, as well as showing that the opposite of that statement, the negation of it, cannot be proved from those axioms and the statement. So in other words, you're trying to show that your set of axioms are consistent, right? Because prior to that, this whole debate, this whole field was plagued with paradoxes, inconsistencies, like talking about the set of all sets and stuff like that. So you got all these weird paradoxes, dozens and dozens of them. And so people were very conscious then that you need to set up a set of axioms that are consistent. That it's impossible from that set of axioms to generate statements, theorem statements or theorems of the form x and second statement, not x. You don't want these contradictions. You don't want from the same set of axioms that it's possible to deduce two statements that are the opposite of each other. You don't want that. That's not consistent. That makes the set of axioms useless, right? So Hilbert concentrated on the problem. Well, how can you decide? How can you decide whether the set of axioms is consistent? Right? You need some mechanism. So Hilbert had this vision of almost machine-like taking a set of axioms and cranking out all possible theorems and showing that you cannot have two theorems that are the opposite of each other. You cannot have contradiction. And that was his big dream. Now, a lot of people just thought that was nuts. The French mathematician, the greatest of his era, Poincaré, the father of, pretty well, what's he famous for? If you keep following me for the later grad courses, you'll certainly hear the name Poincaré, P-O-I-N-C-A-R-E, cute in French. He's pretty well the father of algebraic topology, chaos theory. Well, they're probably two main ones. Anyway, so he, famous French mathematician living around 1900 or so, almost arrived at the same special relativistic conclusions as Einstein. He was just about a year away, just a little behind Einstein. So a universal genius. Somebody, as the story goes, somebody asked Bertrand Russell, the logician, philosopher, British, in his opinion, Russell's opinion, who was the most famous man in France at that time. And Russell said unflinchingly, "Oh, Poincaré." And the person asking the question was surprised because Poincaré had a cousin? Brother? I'm not quite sure. Also Poincaré, a relative Poincaré, who happened to be the Prime Minister of France around the time of the First World War, I think. Anyway, it wasn't the... So the person asking the question was surprised and queried Russell, and then Russell said, no, not the French Prime Minister, the mathematician. Okay, so a famous guy. So anyway, Poincaré was extremely skeptical of the vision, the dream of Hilbert, that some mechanism, some method could be found that would decide whether a set of axioms was consistent. Right? That was the problem. How do you decide the deciding problem, Entscheidung Problem? And let's see, I got to keep popping the stack. And the American logician, mathematical logician, Church and Turing as well. Church was a little ahead of Turing on this line. Church was fascinated by this Entscheidung problem because there was so much at stake. I mean, if Hilbert had been correct, then mathematics would become a branch of engineering. In a sense, you'd just be, having a machine that would churn out the theorems. And Turing's machine, the Turing machine, that was a way to mechanically, in a sense, make deductions. Now, it was Gödel who showed that the whole enterprise was doomed from the start, but it was Church and Turing who showed mechanisms that would allow you to mechanically calculate, so to speak, a statement from the axioms. Now, that's one thing, trying to show that they're consistent, the axiom set is consistent. Well, that's another, but at least going from this set of axioms to some statement, that can be done mechanically, and we've been learning how to do that with the Turing machine. But Church got there a little before Turing. In fact, I think it was Church who gave the first result, some statement that cannot be decided. You can't prove it or disprove it. Can't be solved. And that was a pretty famous result. And we've been talking about it on this board. It's an amazing concept. You can actually prove that something cannot be solved, an unsolvable problem.